Welcome back. So, in the last part we discussed about first law of thermodynamics. We discussed about the essence of the law, that it is a law of conservation of energy, and we discussed about few statements, like we discussed there in a cyclic process the work done will be equal to the heat withdrawn, which means that first law of thermodynamics discusses about only the law of conservation of energy. However, if you ask this question, that suppose if we have nitrogen and hydrogen in a mixture to produce ammonia, at equilibrium how much nitrogen, how much hydrogen and how much ammonia is present, the first law cannot answer. The only answer it can give is through mass equilibrium. We know that there will be a finite amount of nitrogen, hydrogen and ammonia, and we know the total amount of the mixture. However, the equilibrium concentrations cannot be predicted. So, the second law actually yields or answers gives an answer to such questions. Now, to begin with, we will first use the statement of the second law. The second law was mostly developed by a French engineer, Carnot, and then his work was revived by many others, and then they put it in a modern form. So, what we are going to discuss is that modified form of Carnot's work. So, let us first look at the statement of the second law. These statements actually come from natural experience from the work on heat engines. Now, there are two statements I have written here. The first one is known as Kelvin-Planck Statement. It is based on Carnot's work, and it was a revised statement given by Lord Kelvin or William Thomson, who is also known as William Thomson, and Max Planck. The statement says it is impossible for a system to undergo a cyclic process whose sole effect are the flow of heat into the system from a heat reservoir and the performance of an equivalent amount of work done by the system to the surrounding. What does it mean? It means, suppose let us consider I have a heat bath at some temperature. Let us say I am calling this temperature as TH, and then there is an engine which is our system, and this system is withdrawing say some amount of heat from the surrounding, which is in this case the hot bath, and then producing in a work in the surrounding which is equivalent to the magnitude of which is equivalent to the heat withdrawn from the surrounding. Now, we already discussed in the first law that for a cyclic process this is true, but the second law is saying that complete conversion of heat into work is not possible. So, this example shows you that it does not violate first law. However, it violates second law in that here we are assuming the complete conversion of work into heat, which is not possible. Now, if that is not possible, then how much heat or how much amount of work can be produced from a given amount of heat, that we have to work out, and that is what we are going to do in today's lecture. Now, another statement we often say is known as the Clausius Statement. We will discuss about Clausius's work on particularly the irreversibility or the directionality of a process, which is known as Clausius inequality, sometime later. But before that, we will just discuss the Clausius Statement of the second law for thermodynamics, and the statement says that it is impossible for a system to undergo a cyclic process whose sole effects are the flow of heat from a cold reservoir and the flow of an equivalent amount of heat out of the system into an hot reservoir. So, Clausius statement says that suppose I have a cold reservoir and I have a hot reservoir where the temperature of the hot reservoir is greater than that of the cold reservoir, and if I thermally connect it to a system, I connect both of them, Clausius statement says that it is impossible that the system withdraws some amount of heat from this cold reservoir and flow the same amount of heat, which will be same, let me just denote it as Q, to the hot reservoir. So, this is not possible. So, we will see actually why what happens if these laws are actually violated. Now, there is an equivalence between the Clausius statement and Kelvin-Planck statement, but we will not discuss it here. We will first proceed with the Kelvin-Planck statement, and we will show in a minute that if we construct or if we hypothesize a system that violates the second law of thermodynamics, then we can get a complete conversion of heat into work, which is not possible. Now, before going into the details, as I said that all these statements are actually realized in experiments on heat engines, let us first describe what is a heat engine. Now, usually in chemistry, we do not talk too much about heat engines. We usually talk about chemical systems where actually flow of energy into the system or out the system is associated with some chemical transformation. But here usually the heat engines are used in engineering community to understand the efficiencies of various types of engines. However, the concept built in discussing the heat engines will be utilized subsequently to describe the directionality or spontaneity of many chemical processes. Now, let us understand what a heat engine is. Now, a heat engine, by a heat engine we mean that there is an engine which is nothing but our system, and that withdraws heat from a hot reservoir, meaning a reservoir which is at a temperature which is of course hotter than another reservoir which we term as cold reservoir, and the temperature of that we denote as Tc with the condition that Th is greater than Tc, and in the process the system or the engine which is the heat engine takes the some amount of heat and it releases some amount of heat to the cold reservoir, and in the process as a balance it also produces some work. Now, what I have drawn here is schematically means that if I use the first law of thermodynamics, and we can actually give a formulation for this, but before that let us try to understand one important thing, that suppose this system is our already familiar system which is a ideal gas or some gas confined in a cylinder, and where a piston is also act as a boundary between the system and the surrounding. Now, if the gas expands, then the piston will move upward. If the gas contracts, then the piston will move downward. Now, this motion of the piston can be very cleverly connected to a axle, where this motion up and down will cause a rotation of this axle, and thereby you can actually get a rotational motion further, which may run something. Say this may run actually a steam engine. Now, this was actually the first design which James Watt used to design his engine which was run by steam. So, the material which he used was nothing but steam. Now, this was again based on Sadi Carnot's work. Now, try to understand here that if the engine, if we expand the gas and if we do some work, of course, the wheel will rotate, but then we have to also come back because we have to keep it going. Otherwise, there is no point of designing or devising a machine. So, what it means that this engine or this system should work in a reversible fashion. So, this is very important, the reversibility of the working. Now, we say that if there is a reversible process, which means actually it should also work in a cyclic manner, because the system should actually come back to its original state and again expand, then contract to maintain this process and maintain the reversibility. So, in order to maintain the reversibility, we can say from the first law that for any reversible cycle, as we know that the associated change in internal energy should be 0, and from first law it is nothing but related to the heat withdrawn and work done. Now, look at it here. Here actually we have two types of heat. One heat is actually withdrawn from the surrounding and one heat is released to the surrounding. But there are two different surroundings here. One surrounding is the hot bath or hot reservoir, and then what surrounding is the cold bath or cold reservoir. So, the system or the engine takes up the heat from the hot reservoir and releases it to the cold reservoir. So, we can write it in this way and perform some work, of course. So, this Q is nothing but a combination of QH and QC. Now, note that usually we use a convention that for QH we use a positive convention because it is a heat withdrawn from the surrounding to the system, and for QC it has to be a negative quantity because it is released into the surrounding, which is the cold bath here. Or in other words, we can say it slightly differently, that the heat withdrawn from the hot reservoir is nothing but the heat released in the cold reservoir plus the work done by the system. Now, the negative sign here in the first term, which is QC here, indicates that heat is released to the surrounding, which is the cold reservoir here, and the negative sign associated with the W or the work done indicates that the system performs work, because we took a convention that if the work is done on the system, that is a positive work, and if the work is done by the system, that is a negative work. So, in some sense the total amount of heat is partitioned into some amount of heat and some amount of work. That is the essence of second law. What we just said in the previous slide, a statement that complete conversion of heat into work is not possible. I cannot take QH and completely convert it into a work which is equivalent to QH. Always whenever I am withdrawing some heat, some amount of heat will be always lost, which is QC, and then the rest will be produced, rest will be utilized to produce work, which means if we can make the QC to be 0, then we can approach the limit, which is QH is equivalent to the negative of work done, negative in the sense that it is work done by the system, but that is not possible. We will always have some finite amount of QC, and that will reduce the efficiency of the heat engine. Now, how will you calculate the efficiency, keeping in mind that this efficiency of the system or the heat engine has to be in such a way that the system or the engine runs in a cyclic fashion and in a reversible cyclic fashion. Now, the first answer to this problem was given by a French engineer, as we already told, Sadi Carnot, and then Carnot proposed hypothesized a mechanical cycle by which one can withdraw heat from a hot body and release it to a cold body and simultaneously perform some work using a system. So, we will first try to understand it in our already familiar pressure volume diagram, because that will tell us how much work has been done or has been performed in a cyclic process, where the cycle is initiated by something like withdrawal of the heat. Now, suppose we have some change in state of the system, say from state 1 to state 2, and in this process the heat is first withdrawn. Now, this is an arbitrary line which I have drawn going from arbitrary path, because remember that the amount of heat withdrawn will be dependent on the path, because heat is a form of energy and it is a path function. Now, think about it, like if we have to withdraw heat from a source, and then if this process going from 1 to 2 is not an isothermal process, meaning that the temperature of the system actually gets increased in the process, then we can say that this transformation or the transfer of the heat from the outside must be irreversible, because if it is happening at an increase in the temperature, then such flow of heat has to be irreversible. In order to maintain reversibility, because we have to maintain it, remember, because the system has to be restored in its original condition, then we assure one thing, that this path has to be an isotherm. So, this cannot be an wavy line that as we have drawn here. The first part has to be some isotherm where the system actually withdraws heat from the surrounding, which is the hot reservoir, keeping at the same temperature of the surrounding or the hot reservoir. Similarly, by the same token, when the system releases it, remember it will release it to a cold reservoir, and which is at a temperature Tc, and since Th is greater than Tc, then we can say that by the same token the system must be brought in contact with the reservoir, but before that the system's temperature has to be equal to the cold reservoir's temperature. So, means these two are two isotherms has to be the steps at which the system is withdrawing heat from the hot reservoir or the system is releasing heat to the cold reservoir. Now, since Th and Tc are different, these two, of course, these two isotherms are different isotherms, and I have drawn the isotherm for releasing the heat Qc to the colder body at a position which is lower than the earlier isotherm. The reason is Th is less than Tc. Now, so this is basically a reverse process, but we have to connect it. Remember, in the first process we said the system is withdrawing heat from the reservoir keeping at a temperature Th. It is an isothermal process. Then we said that there is another process where the system is releasing the heat Qc to the cold reservoir keeping at a temperature Tc. Now, in order to achieve these two things, in between the system must make a transition where the temperature of the system goes from Th to Tc. So, what we said is that earlier the system was in thermal equilibrium with the hot reservoir, and then we have to cool down the system so that it comes in thermal equilibrium with the cold reservoir, so that we can do some isothermal expansion in this case and then again an isothermal compression. So, we need actually two adiabats to connect these two isotherms. And the real meaning here is that the adiabats are required to change the temperature of the system from TH to TC and then from TC to TH. So, we have considered a cyclic process in this case. Now, this is the actual formalism which Carnot came up with. Now, let us try to understand how much work is done for each step of the process, so that we can calculate the total work done in the process. Now, let us also designate that we will call this as step 1, this as step 2, this as step 3 and this as step 4. And we can just quickly redraw it once again, so that we can always refer. So, this is basically the Carnot, known as Carnot cycle. So, it is going from state 1 to 2 by isothermal expansion, then 2 to 3 by adiabatic expansion, then 3 to 4 by isothermal compression, then 4 to 1 again by adiabatic compression. Now, this is step 1, this is step 2, this is step 3 and this is step 4, and this cycle is continued, and the system or the heat engine continuously take for in each cycle QH amount of heat and releases QC amount of heat. So, let us now try to understand what is the work done in this entire process. Now, for that we will use the first law of thermodynamics, which tells that du is nothing but d cross q plus d cross w, or we can actually use the finite change relationship, because this is for the differential change, but since when the system is going from state 1 to state 2, it is a finite change. So, we will better write it as delta u is q plus w. Now, in the step 1, what it does, think about it, it is an isothermal expansion. So, in the isothermal process, since internal energy is a function of temperature only, delta u for step 1 will be 0. So, from first law, the left hand side of this equation is 0, is equal to the heat associated in this case is nothing but QH, and the associated work I am writing as W suffix 1. Similarly, in step 2, we have an adiabatic compression. Now, for adiabatic compression, there is no heat change because it is an adiabat, and then instead of delta u, if it is an ideal gas, we could write it as Cv dt between the states 2 to 3. If it is an 1 mole ideal gas, we can actually write it as Cv bar dt, assuming that Cv does not depend on the range of the temperature over which the transformation was made. And then there was a term del u del v T dV, but we already said that term is 0 for ideal gas. So, that should be equal to 0 because QH is 0 for an adiabatic process plus W2. Similarly, for step 3, remember that again there is an isotherm, but now heat is released, QC amount of heat is released. So, I have to use a negative sign plus W3, and then again in step 4 there is another adiabat, and remember that in this case I am going from state 4 to state 1 dt, and which is nothing but 0 because it is an adiabatic process. So, associated heat exchange is 0. So, W4. So, the total W can be obtained by adding all the W's, and let us see what is the total work done. So, it is basically W1 plus W2 and so on. So, the first equation gives us, in the first process it is minus QH, the second equation gives us it is CV, and integral of dt between the limits 2 and 3. Let us suppose that the what happened between 2 and 3, think about it. Initially the system was actually at a temperature TH. So, the initial temperature of the system was TH and the final temperature of the system was TC during the process 2 this has happened. So, this will be nothing but CV TC minus TH, and then for the third process again we will have plus QC, and again in the fourth process we will have CV TH minus TC, because here the final temperature is again TH for the fourth process. These are the two adiabats and the initial temperature is TC. So, we will use the molar quantity. So, we are using CV bar notation. Now, let us try to understand. So, what is this total energy that we total work done that we got. Now, the efficiency of an heat engine is defined in the following way, which is denoted as sometimes E, or some textbook write it as eta, which is denoted as how much work is produced in the process and how much heat has been withdrawn in the process. Now, remember the work produced in this case I will write it as minus W, because it is work produced by the system, and the heat withdrawn in this case is QH, because it withdrew the heat only in the first step. So, in the according to the second law, this efficiency cannot be equal to 1, because if it is equal to 1, then the magnitude of QH will be equivalent to magnitude of W, which is not possible. Complete conversion of heat into work is not possible. So, this efficiency should be always less than 1. Now, let us try to calculate what was the efficiency that we just got by in Carnot cycle. So, we already see here that these two quantities cancel with each other, because they just have opposite sign. So, ultimately we get something very interesting, which is QC minus QH, and then if we just plug in into this equation, we will get that it is QC minus QH, but with a negative sign. So, it will be QH minus QC, and that is the expression for minus W. So, ultimately we will get the efficiency to be equivalent to QC by QH. Now, this is the expression for efficiency of a Carnot engine if the engine was, or the material of the engine, active material of the engine was an ideal gas. Now, think about it, that if we had QC close to 0, meaning if we had a absolute 0 sink or heat sink where actually I am dumping the heat, then the efficiency goes close to 1, or we could have made the QH, the heat source, to have infinite having infinite temperature. There also we will see that we can get the efficiency to be closer to 1. So, right now we have written it in terms of the heat withdrawn, but we will write it in terms of also the temperature of the cold and the hot reservoir. Let us see how we can get to that expression. So, what we just said is that let us just focus on the step 2 and step 4, which are basically the adiabats, which are these two steps where we are going from 2 to 3 and 4 to 1. Now, think about it. In this case, what was the total cyclic, this is a cyclic process, of course, the entire process will mostly to get to that relationship between heat withdrawn and the temperature at which it is withdrawn, we need to again consider the cyclic process. Now, for every cycle, let us just write it in this way, that I have for any cyclic process dq is d cross q plus d cross w, which follows from the first law. Now, I will just write a suffix reversible here in order to denote that it is for a reversible process, and usually for reversible process all the dq's should add up to 0, that is well known. Now, let us try to for a reversible cyclic process, by the way, but in this case actually reversible isothermal process it will be 0, not for any cyclic process, but in this case we will show that this term also will go to 0. Now, before going to that, what is du? Du is nothing but the Cv dt and d cross q reversible, we are just keeping it as such, and then I have the reversible work done, that minus it is P opposing dV. Now, each of this term, it's basically what the way we have drawn it here, we have drawn the cycle, this is the Carnot cycle, and we have written an expression for the entire cycle itself, but the cycle has actually 4 parts. Now, a cycle means there was a cycle for du, there is a cycle for d cross q reversible, there is a cycle for d cross w reversible. That is what we have written here. However, remember, each of this term actually can be split into 4 terms because there are 4 steps. Now, for example, in the first case Cv dt was 0 because it was isothermal, and then we had some Cv dt which is basically Cv T, the final temperature was Tc minus Th, then again it was 0 for the third step, and in the fourth step it was Cv Th minus Tc, which basically cancelled out. And then let us just focus on this term which says that P opposing dV. Now, usually not usually for any isothermal process or any adiabatic process also, since they are both reversible, the P opposing can be set to be equal to the pressure of the system, because actually these are all reversible. Remember that this path is a reversible isothermal path and this path is a reversible adiabatic path. So, we can write it as minus P dV, and using the formula we can just write for the ideal gas it is nRT by V dV. Now, we can divide both sides by T to get an equation something like integral Cv dt by T is equal to cyclic integral of d cross q reversible by T minus nR cyclic integral of dV by V. Now, what is the value of this? In the first case, you will have some pressure volume work, and first step 1. So, that will be minus nR ln say V2 by V1, where V2 is this volume and V1 is this volume, and then you can actually work out for each step. However, you will figure out that they all cancel each other. Why? Because it is a cyclic process. Since it is a cyclic process, you can easily figure out that this term also goes to 0, and we already told that this term also goes to 0. So, what we get is this term also should be 0, dq reversible by t over a closed cyclic path. Now, we have a very interesting situation here. We see that d cross q is not an exact differential. So, for any cyclic process, we already discussed that d cross q is not 0 when we discussed about the first law, and then we said similarly d cross w was also not 0, and then we added them and defined that, found out that their addition is 0, and from there we got a quantity which is du. Cyclic integral of that was 0, that is why you called it as an exact differential. Here we are getting similar situation. We see that d cross q divided by t, I should maintain this notation, d cross q reversible divided by t is 0. So, for any cyclic path, which means although d cross q is not a state function, d cross q reversible by t is a state function, and that we are denoting as ds. So, we can write it in a compact form that cyclic integral of ds is equal to 0, where S is known as entropy of the system. Now, again, entropy of the system does not have any meaning. We only talk about change in entropy of the system. This is the differential change, and we are talking about a cyclic path. So, we see that entropy is an state function, and entropy is defined as the reversible exchanged divided by the temperature at which it was changed. Now, we will proceed with the entropy in a while, but before that we will first discuss something known as Carnot theorem. Now, this is again based on a conceptual understanding how a heat engine works. Now, the theorem tells you that no heat engine can be efficient than a reversible heat engine. So, our reversible heat engines are maximal efficient engines. Now, why how to understand this process? Let us consider as before that there is a reversible engine which we denote as say some system or engine which is reversible, and it is withdrawing heat from the cold reservoir, and it is performing some work, and also it releases the heat which is say QC to the cold reservoir. So, it is withdrawing heat from the hot reservoir and releasing heat to the cold reservoir. Now, since it is an reversible engine, what it means is that it can also work in a reversed direction. Now, let us hypothesize a situation that we have a source or heat sink at temperature Th, heat source sorry, and a heat sink which is at temperature Tc. So, this is nothing but a hot reservoir, and this is nothing but a cold reservoir, or sometimes we call it as a source or heat source, and this we call it as a heat sink. Let us have our irreversible engine which is withdrawing heat from this hot reservoir and transferring the heat to the cold reservoir, and let us couple to it our reversible heat engine which actually is now working in a reverse direction. Since it is reversible, we can always reverse its direction. Now, suppose the amount of heat which this reversible engine is dumping to the hot reservoir is the same amount which the other engine is withdrawing from the hot reservoir, and we also couple these two reservoirs. Now, the efficiency for the reversible engine will be nothing but 1 minus, if we write it in terms of the temperature of that, we are yet to prove that relationship. We can write it as temperature of the cold body minus temperature of the hot body. Similarly, for the efficiency of the other engine, for any engine actually we should write it in this way. Now, it is not necessary this at this point, so we can also bypass this relation. So, we can write the efficiency of our reversible engine with the original definition, that it is the work done divided by the heat withdrawn. In this case, the heat withdrawn is QH. It will be not QH, it will be some other Q, which is say QC, and then for the irreversible engine it will be the work done divided by the heat withdrawn, but the heat withdrawn in this case is QH. And since we know that we have said, remember that these two QHs are same, meaning the heat withdrawn by the irreversible engine is similar to the heat dumped by the reversible engine. And since QC or the reversible engine efficiency, if we assume that it is more than the reversible engine efficiency, we can easily get a feeling that QH should be greater than QC. Now, what does it mean? That means it is actually taking the net effect of this composite system is that as if it is withdrawing some heat from the cold reservoir, and then the second engine does some work, part of it is transferred to the first engine because it has to balance this QC and QH, because QH is greater than QC. So, part of this work is converted to balance to add up with this QC to give QH, which is being transferred to the hot reservoir, and again from the hot reservoir this engine is taking up QH heat. So, from the hot reservoir we see that there is nothing withdrawn or gained, because the heat deposited by the reversible engine is the heat which is withdrawn by the irreversible engine. So, everything is happening with respect to the cold reservoir, and what we see here is that the net effect is withdrawing the heat somehow from the cold reservoir and performing some work, so which violates the Kelvin-Planck statement. So, this cannot be possible, which we conjectured, or the reversible engine cannot be less efficient than the irreversible engine. Now, you can similarly argue that if I had two reversible engines, and you can similarly show that if I have a reversible engine 1 which is more efficient than the reversible engine 2, you can make an analogy, but then one can easily switch this in the position. You can put the reversible engine 1 here and 2 here, and then you can get another relation which is basically irreversible 2 is greater than irreversible 1, which means these are contradictory statement, and this leads to the another way of looking at the Carnot theorem, that between two same temperatures a reversible engine must be more efficient than an irreversible engine. So, before we conclude, we will just quickly discuss one particular relation. So, we had already discussed that cyclic integral of d cross q reversible by T is 0. Now, from the Carnot cycle, we know that for the first step, what is the value of this? For the first step, it is QH drawn at a temperature TH. In the second step, it was adiabat, no heat was withdrawn, and then in the third step again it was minus QC because the heat was released at a temperature Tc, and in the fourth step it was again 0. So, overall what we are getting is QH by TH minus QC by TC, and then since the entire thing is equal to 0, we can write QC by QH is nothing but TC by TH. So, the equation for efficiency E or eta we could write 1 minus QC by QH, which is equivalent to writing 1 minus TC by TH. Now, you can see that if TC approaches close to 0, the efficiency goes close to 1, or if TH approaches close to infinity, then also the efficiency goes to 1. However, for finite cases, since TC is less than TH, we will have some fractional value for this, and the efficiency will be always less than 1.